Hey everyone, Math 103. This is section 6.2, least common denominators. You may have heard that expression before. That's what we need. We're going to add and subtract fractions, which is what we're going to be doing in the next section. So this section is critical. Our two objectives are to find the least common denominator for a list of fractions and to write equivalent rational expressions. So what that means is we're going to first find the LCD of a couple of fractions, and then we're going to rewrite both of those fractions having that LCD as the denominator. So let's see how this is going to work. First thing we need to understand is the idea of a multiple. A multiple is what you get when you take any number and you multiply it by 1, 2, 3, and so on. So for example, if we want to find the multiples of 8, we're going to multiply 8 by 1 to get 8. 8 times 2 is 16, 8 times 3 is 24, and we can continue on in that fashion as long as we need to. So we can write out the multiples then using a comma-separated list, 8, 16, 24, 32, and then some ellipses showing that it goes on. So this is what we're going to use to find the LCM of two numbers. So to find the LCM of 9 and 12, all right, LCM being least common multiple, we're going to write out the multiples of 9. So we got 9, 18, 27, 36, and it goes on like that. And for 12, we got 12, 24, 36, and it goes on like that. So basically we're counting by 9s, counting by 12s. So once we have our list, now we want to take a look at this list and find the smallest, remember least common multiple, so we want the smallest number. So let's match between these two lists. All right, 9 doesn't have a match, 18, no. 36 does though. 36 is the first match between those two lists of multiples. So that is the LCM of 9 and 12. So try this method out on your turn number 1. So the multiples of 10, we got 10, 20, 30, 40, 50, and 60. And for 12, we got 12, 24, 36, 48, and 60. So the first match in that list is 60, making the LCM of 10 and 12, 60. So now we're going to work with some variable expressions. So to find the LCM of variables, select the largest exponent among the matching bases. So here's two expressions with matching bases x. So we're going to select the largest exponent amongst those two. So the LCM of x to the 5th and x to the 7th is x to the 7th. So the larger of the two exponents. Your turn number 2. Find the LCM of x to the 8th and x to the 5th. Larger of the two exponents is 8, so LCM is x to the 8th power. And the next page, you see the LCM shortcut. The LCM of x to the a and x to the b is x to the a if a is greater than b. So select the largest one. X to the b if b is greater than a. Now we're going to look at the LCM of two or more monomials. So now we've got potentially, coefficients and variable parts together. Next example, we're going to find the LCM of 16 x to the 4th and 20 x to the 7th. So we're going to do the numbers and the variable parts separately. Start with the numbers. Listing the multiples, you got 16, 32, 48, 64, and 80. And for 20, 20, 40, 60, 60. Oh, I messed up. Get rid of that, 60 and 80. And the first match is 80. So the LCM of 16 and 20 is 80. All right, now we'll go on to the variable parts. Select the larger of the two exponents. 7 is larger. So that makes the LCM 80, x to the 7th power. Your turn, number 3. So we'll start with the numbers. 9, we got the multiples here, and 15. And the first match is 45. Now these two variable parts, we got matching bases x, so we'll select the largest exponent, 6. So the LCM equals 45 x to the 6th power. So any number of numbers and variables can appear in these expressions. So we're going to take things one piece at a time. We're going to start with the numbers, 14 and 12. All right, there's our multiples of 14 and 12. First match is 84. Now we're going to take things one base at a time. We're going to look at the x's first. The larger of the two exponents here, we got a 1 here and a 3, so 3 is the larger exponent. So we'll have x to the 3rd power. All right, now we got y squared here. We don't have a y over here. And this can be a little confusing because with greatest common factor, we just exclude the y. But with the least common multiple, we have to exclude every single variable. So we're taking the larger of the two exponents. Just consider this to be y to the 0 power. The larger exponent then is 2. So our LCM is 84, x to the 3rd power, y squared. Your turn, number 4. So doing the numbers, you get an LCM of 24. Now for the variable parts, comparing the like bases, x to the fourth and x squared, x to the fourth is the bigger power. And out of the y's, we have y to the first and y to the fifth, so y to the fifth, larger exponent, 24, x to the fourth power, y to the fifth. Now we can do any number of monomials as well. The process will be the same though. So now we're going to find the LCM of 12, x to the 6, y squared, 16, x to the 7th, y to the 3rd, and 8, x to the 3rd, y to the 4th. So now everything we do, we just do with 3. So we're going to do 12, 16, and 8. All right, now 16 and 8. And the first match between all three, now since we have three numbers, all three have to match. First match is 48. So that will be the coefficient of the LCM. Now we're going to do the x variable, x to the 6th, x to the 7th, x to the 3rd. Largest exponent is 7. Now we'll do the y's, y squared, y to the 3rd, y to the 4th. 4 is the biggest exponent. So our LCM is 48, x to the 7th, y to the 4th. Your turn, number 5. So for the numbers, LCM is 36. Now for the variables, we got x to the 4th and x to the 3rd. 4 is the larger exponent, so we'll keep that. And y to the 5th, y to the 3rd, y squared, we'll take y to the 5th. Our LCM is 36, x to the 4th, y to the 5th. And now we're going to find the LCM of expressions with binomials in them. And these are going to act just like variables. So here's our two expressions, x plus 1 times x minus 4 to the 5th power. That's the first one, and the second expression is x minus 4 squared times x minus 5 to the 3rd power. So first thing we're going to do to find the LCM is write down every unique factor, every unique binomial. So x plus 1, no exponents when we do this, x minus 4, and x minus 5. All right, there's all of our bases. Now, we look through these and we select the largest exponent for each base. X plus 1, that's the only one, first power, so that stays. And we've got two x minus 4 expressions. So we got second power and 5th power. Largest exponent is 5, so this one gets a 5 exponent. Now we only have one x minus 5, and that's to the 3rd power, so that's what we'll have down here. So the LCM is this. Your turn, number 6. All right, there's our three unique bases. Now look at the x plus 6. We got the first power and fourth power, so 4 is larger, so we'll take that as the exponent. X minus 2, that's the only one we have, and that's to the third power. So we'll keep that. And x minus 3, that's the only one, and that's the first power. So there's the LCM. X plus 6 to the fourth, x minus 2 to the third, x minus 3. Our next example, we're going to mix up variables and binomials. But as you'll see, the process is exactly the same as long as you just look at all the variables and binomials as just being bases. They're bases which we're going to put an exponent on. But they act exactly the same. So we're going to find the LCM of those two expressions. So let's start by listing the bases, just like we did with the binomials when they were by themselves. Right now we got some variables in here, but they're still just bases. So we have an x base, we got a y, we have a z, and now amongst the binomials we have x plus 3, x minus 5, and x plus 7. So the first step should always be just create the list like that of all your bases. Now we're going to find the largest exponent for each one. So for x's, we have 2 and 4. 4 is larger. 4 goes down here. For the y's, we have 3 and 1. 3 goes there. With z, we only have one of them. That's to the first power, so that's just going to stay the first power. Now the x plus 3, we have one of those. That's the first power. X minus 5, we have 2 of those, and 3 is the larger power, so we give 3 there. And x plus 7, that's to the first power. So there's our LCM. Your turn, number 7. So there's all our unique bases, x, y, x plus 4, x plus 6, and x minus 5. Now, we only have one x. That's the fourth power. We got 2 y's. Larger exponent is 3. We've got 1 x plus 4. That's to the first power. We've got 1 x plus 6. That's to the second power. And for the x minus 5s, we have 2 of those. Larger exponent is 2. All right, next up, we're going to be doing basically the same thing, but starting with a little different form. I'm going to look at some actual fractions here. So there's a couple of fractions. We're going to find the least common denominator of those two fractions. So the first thing we need to do is factor the denominators. 8x, that's just 8 times x. Not much to do there. But x squared plus 4x equals x times x plus 4. So we've got 8 for a coefficient. We have 1 down here, so we know that 8 will be the coefficient on the LCM. Now we've got x here and x here, so those got to bring down an x base. And then we need x plus 4. Now everything has an exponent of 1, so we're done. 8x times x plus 4. Your turn, number 8. All right, now we've got 4x and x times x minus 5. So again, we've got a coefficient of 1 here and 4 here, so we're going to get 4 for the coefficient of the LCD. We got 2 x's, they're both to the first power. And we have x minus 5, also to the first power. So that's 4x times x minus 5. That would be the least common denominator of those two fractions. We may have to do some factoring of trinomials. Right, so there's our two denominators. We're going to start by factoring. So this one turns into 1 over x plus 5 squared. Right, got a perfect square trinomial. And here, x plus 5 times x minus 2. All right, now we're going to find the least common multiple of those two denominators. So our two factors are x minus 2 and x plus 5. Largest exponents, x minus 2, we just have one of those, and it's exponent 1. X plus 5, we got an exponent of 1 here and 2 here. 2 is the larger one. So the least common denominator for those two fractions is x minus 2 times x plus 5 squared. Your turn, number 9. So there's the factored form of those two denominators. We've got two bases, x plus 7 and x minus 3. X plus 7, that's the only one. Exponent of 1 there. X minus 3, larger exponent is 2. So our LCD is x plus 7 times x minus 3 squared. So now that we can find the least common denominator in a couple of fractions, now we're going to take both of those fractions, we're going to find the least common denominator, and then we're going to convert both fractions to having the same denominator. Once we know how to do that, then we'll be ready to add and subtract rational expressions together. Our first example, we are going to rewrite 5x over 3x minus 2 and 4 over x plus 5 in terms of the LCD, least common denominator. Now let's look at these two denominators. Right, we have a binomial here and a binomial here. They're different, and they're both to the first power. So that means the least common denominator is just going to be their product. 3x minus 2 times x plus 5. Alright, so this is the denominator we want for both of these fractions. So how do we convert these fractions to have that denominator? We're going to multiply by the missing factors. This fraction has 3x minus 2 already. Right? We already have this one, so we don't need any more of those. But we're missing x plus 5. So that means we're going to multiply this fraction by x plus 5 over itself. You have to multiply it by it over itself because if we just multiply by x plus 5, we're changing the value of this thing. X plus 5 over x plus 5 is the value of 1. Anything divided by itself is 1. And when we multiply anything by 1, it doesn't change the value. All we're changing is what this fraction looks like. All right, now we got to do the numerator. 5x times x plus 5. Now we're going to distribute 5x into x plus 5. So 5x times x is 5x squared. And 5x times 5 is 25x. All right, there's our numerator. And the denominator, we're going to leave in factored form. Do not FOIL. All right, there's the first fraction. Now we're going to do the second fraction. 4 over x plus 5. So we're going to multiply by what this fraction is missing in the denominator. We have the x plus 5 already. What we're missing is 3x minus 2. Distributing 4 into 3x minus 2, that gives us 12x minus 8 over our common denominator. Doesn't matter which order we write these in, I usually just write them in the same order. So 12x minus 8 over our least common denominator. Your turn, number 10. So just like with the example, we have two binomials here that don't match. So we've got two unique bases. So that means our least common denominator will be 2x plus 5 times x minus 7. So first fraction, 3 over 2x plus 5. All right, we've got that binomial. We're missing x minus 7. So we're going to multiply this by x minus 7 over x minus 7. Distributing 3 into x minus 7, we get 3x minus 21. And then leave that denominator in factored form. For the second fraction, we got 6x over x minus 7. So we've got the x minus 7, we're missing 2x plus 5. All right, now distributing in, it gives us 12x squared plus 30x over x minus 7, 2x plus 5. Next example. Three over 5y to the third and 2 over 7xy. So first thing we're going to do is, just as we did before, we're going to start with the coefficients, 5 and 7, and list the multiples. And the first match is 35. So that's going to be the coefficient on the least common denominator. All right, now we'll look at the variable parts. We only have one x to the first power, so that's going to stay in the LCD, and then y and y to the third, the larger exponent, is the third power. So there is our LCD. All right, now we have to make each of these denominators equal to 35x times y to the third. So for the first fraction, what we multiply by, you take the LCD and divide by what we have. 35x y to the third divided by 5y to the third. All right? 35 divided by 5 is 7. Keep the x. And then y to the third divided by y to the third is 1. So what we need to multiply by is 7x. 3 times 7x is 21x. Multiplying all this out, we get 35x y to the third. So now we've got our LCD as the denominator. Next up, 2 over 7xy. All right, what are we going to multiply by? We're going to take the LCD and divide by 7xy. 35 divided by 7 is 5. X divided by x, those cancel. Y to the third divided by y is y squared. So we need to multiply by 5y squared over 5y squared. 2 times 5y squared is 10y squared for the numerator. And the bottom we got 35x, and y times y squared is y to the third power. So there's our two fractions with the same denominator. And now we're ready to go ahead and add and subtract those together. Your turn, number 11. Well, least common multiple of 7 and 3 is 21. A little shortcut you can use if you have two prime numbers like this, just multiply them together. 3 times 7 is 21. Now, if the variables, largest exponent on x is 2, so we got 21x squared, and for the y, also largest exponent is 2. So the LCD is 21x squared y squared. Right, now we're going to multiply by what is missing here. So we get that by taking the LCD and dividing by the denominator. 21 divided by 7 is 3. X squared divided by x squared, those cancel. Y squared divided by y is just a single y. So we need to multiply by 3y over 3y. Multiplying the numerators, we get 15y. And the denominator, we got 7 times 3 is 21. X squared, y squared. Now, second fraction. 2x over 3y squared. Take the LCD, divide by the denominator. 21 divided by 3 is 7. X squared divided by 1 is x squared, so we'll keep that. And then y squared divided by y squared, those cancel. So we're multiplying by 7x squared. All right, multiplying across, we get 14x to the third power divided by 21 x squared, y squared. So there's our two fractions with the same denominator. So we got x squared over y times y plus 7 and x over y plus 7 squared. So this one's already factored for us. All right, so the LCD, all we have is variable parts. We have two bases. We have y and we have y plus 7. For the y, it's only 1 to the first power. For the y plus 7, we have 2 of them, and the larger exponent is 2. So the LCD is y times y plus 7 squared. All right, now let's examine this first one here. We've got x squared over y times y plus 7. So if I take this LCD and divide by y times y plus 7, the y's cancel. One of the y plus 7's cancel, but we still need one more. So we're going to multiply by y plus 7 over y plus 7. And that gives us x squared times y plus 7 on top, and y times y plus 7 squared in the denominator. And it's okay, as far as I'm concerned, you can leave these in factored form. Distributing is optional. Whatever you do, don't distribute either, because we got an exponent here, so can't distribute. All right, the other fraction, x over y plus 7 squared. All right, if I take the LCD and divide by the denominator, the y plus 7 squareds are going to cancel, leaving only a y. So we're going to multiply this by pi over y. So that gives us xy over y times y plus 7 squared. Your turn, number 12. So examining our two denominators, we got a single x, all right, there's a base that's going to be in the LCD, and the other base is y plus 2. The larger exponent of y plus 2 is 2, so our LCD is x times y plus 2 squared. All right, first fraction, 3 over y plus 2 squared. What we are missing, we already have the y plus 2 squared, we're missing the x. So we're going to multiply by x over x. It's the same thing you get if you take the LCD and divide by the denominator. These cancel, leaving just the x. So we get 3x on top and x times y plus 2 squared in the denominator. Next up, we got y over x times y plus 2. So So we have the x, and we have one of the y plus 2's. We're missing the other one. So we're going to multiply by y plus 2 over y plus 2. So on top, we got y times y plus 2. And on the bottom, we get x times y plus 2 squared. Next ones are going to require some factoring. Right, we got a difference of squares here, so we can rewrite this one as 4 over x plus 5 times x minus 5. Now we have two unique bases. We have x plus 5 and we have x minus 5. So that means our LCD is x plus 5 times x minus 5. Now this one already has the LCD, so we're done there. We don't have to change that one at all. But this one is missing the x plus 5. So we're going to take 3x over x plus 5 times x minus 5 over x minus 5. All right, now you can either leave it in factored form or distribute. Which one is appropriate? It really depends on what we're doing, so do it either way. So that gives us 3x squared minus 15x if we do distribute in the numerator. And at the bottom, x plus 5, x minus 5. Just remember, don't FOIL the denominator. Your turn. Oh, yep. Are we done? Yeah, we're done. Your turn, number 13. So factoring the denominator here, we get x minus 3 times x plus 2. So that means our two unique factors are the LCD, x minus 3 times x plus 2. All right, no higher exponents. So this one, we already have both of them, so we're all set there. We just need to change this one by multiplying by the missing piece, x plus 2 over x plus 2. That gives us 7x plus 14 over x minus 3 times x plus 2. So this is a skill we will need to do what we're going to do in section 6.3, which is adding and subtracting rational expressions. So this is a critical skill, and I hope you all go and practice. See you.